Hi everyone, I'm Alexis, and the work I'm presenting to you has been performed in collaboration with Guanyu, Lander Burgelman, and Frank Verstraete. First and foremost, we would like to thank the organizers and the content committee for giving us the opportunity to present our work at this wonderful but online conference. So before going into the details of our talk, I'm first going to give some motivation and some background on topological quantum error correction and why one might want to study it. So in 1997, Kitaev came up with a brilliant idea that anyons could be used to do fault-tolerant quantum computation. And broadly speaking, this has led to two different streams of research, let's say. The first one being passive topological quantum computation. So here you would encode information in the ground space of some physical system, which is protected by an energy gap at 0 temperature. Of course, if you exceed temperature 0, you would get some thermal excitations, which you must need to correct. And importantly, in these systems, non-abelian anyons can occur. The second thing that came out of this is the active quantum error correction. So here you're working with a system of qubits, which are encoded in some code space defined by a set of stabilizers. You then actively measure these stabilizers, and whenever some of them are violated, you use error correction to fix that. What we want to do is study active error correction, but with a non-abelian code. So we have a system of qubits, and we're looking at the code space defined by a set of commuting projectors. These are no longer the product of Pauli operators, but I'll come back on that later. And then importantly, an important feature is that noise will result in some of these projectors being violated, and these defects will behave like non-abelian anyons. So we have two goals. First, we want to construct such a non-abelian code of qubits, and then design all the necessary circuits for measurement and correction in this code. And then we want to be able to classically simulate this code to find an error threshold. For this, we'll be using three things. There is quantum error correction, there is topological quantum field theory, and then there's tensor networks. And it's only by combining these three ingredients that we're able to solve the problems that we want to solve. So let's take a moment to consider the ups and downs of abelian and non-abelian codes. So the upside of abelian codes is that these are very simple, in the sense that these are stabilizer codes with low-weight local stabilizers. So these have been very well studied, continue to be very well studied, and they have very high thresholds. This makes them very attractive candidates for eventually realizing a fault-tolerant quantum computer. But they also have a big downside, which is that in 2 dimensions, they cannot perform a universal set of gates within their code space. So they need to be complemented by some extra scheme to perform a non-Clifford gate, either magic state distillation or code switching to a high dimensional code. It's never free. There's always some some overhead when you want to do this. The alternative is non-abelian codes, and they have the big advantage that in 2 dimensions, some of them are able to natively perform a universal set of gates. They're also a way to go beyond the paradigm of stabilizer codes. There is no such thing as free lunch, so the price you pay for this is that these codes are very complicated. As I mentioned before, these are no longer stabilizer codes. Instead, they're defined by a set of commuting projectors, and these have a much more complicated structure than the product of Pauli operators. These codes are also very hard to simulate classically, and this is the main reason why there has been very little results on such non-abelian codes. There is very good reasons to study them. It's 2-dimensional codes with a universal set of gates within their code space. However, they're so complicated to simulate that maybe many people thought that either it would be completely impossible, or that if you could eventually simulate them, that the thresholds you would find would either be non-existent or be very small. We will see that this is actually much better than what people expected. So we're building upon a number of other works, notably the following four. So there's the work by Koenig, Kupperberg, and Rijkaard, where they introduced Turaev-Viro codes. Then there's the work of Bonesteel and Di Vincenzo, who designed measurement circuits for the Levin-1 operators. There's the PhD thesis of Feng, who introduced some trick to fix violated vertices. I will talk about this later. And then there is the work of Burton, Brel, and Flamia, who studied a phenomenological model of Fibonacci onions and found a threshold for such a code. We used certain of the techniques they use in their simulation to simulate our microscopic model. So let's go on and talk about the code that we used. The code we used is based on the Levin-1 model. So let's start with the regular Levin-1 model. So it's defined by a set of commuting projectors. There's projectors, there's vertex terms, QVs, and then there's plaquette terms, which in general all are 12 body operators. And these are defined using the data of a unitary fusion category. Now this Hamiltonian looks an awful lot like the surface code or the toric code Hamiltonian. And the reason for this is that if you use the right category for defining this model, you end up with exactly the surface code. This is actually a generalization of the surface code on a trivalent lattice. So if you would use the right input category for the surface code, you would see that instead of qubits, you have a system of qubits. So you have like two states, occupied and non-occupied. And then your vertex term impose some fusion rule in every vertex, which in this case is that there is no branching or no strings that are allowed to end. So you would get configurations as the one shown here. And your ground state is then a superposition of all types of configurations with loops in all shapes and sizes. We'll be using another category to define our model, the Fibonacci category. This also has only two string types. So it's again a code of qubits. But now the fusion rules allow for branching. So your ground state will be a superposition of loops, including some branching structure like the configuration shown here. For further reference, I need to introduce the F matrix. So the F matrix is something that comes out of this unitary fusion category that you use. And you can think of this as a way of recoupling your strings, which relates configurations of different loops. So instead of the regular Levin-1 model, we'll be using a slightly modified one. And this modification is that we add a tail edge inside every plaquette. So you'll need 2 extra qubits in every plaquette. The reason for this will become clear later on. But here are some important properties we will use for this model. The first one is that localized excitations behave like doubled Fibonacci onions. So there's 4 types of onions. One of them is the trivial one, and then there is 3 non-trivial anionic excitations. The second property is that inside the subspace, where all your vertex conditions are respected, we call this the stringlet subspace. Inside the stringlet subspace, the onion charge of a single plaquette is a well-defined quantum number. So you can write down a projector that projects on the different possible onion charges in one plaquette. The way we construct these projectors is by using something called the tube algebra from topological quantum field theory. And you can think, this is an operator algebra, and you can think of its generators as gluing this snail-like thing that we call a tube onto this tail edge. So to translate this as an action on these qubits, you would use a series of these F moves to transform this shape back into the normal lattice. So if you do all these steps, you would end up with the following operator. And this tube algebra is pretty neat because a very useful thing is that the central idempotents of this algebra are exactly the projectors onto the different types of anions you can have. So this means that if we combine if we take the right combination of these operators O, you get projectors on the different onion sectors. So in our case, these look as follows. So there is some normalization condition that I left out. But you see, it's just combination with certain weights of these different types of tubes. Once we have these projectors, this means we need to write down quantum circuits for measuring these things. And this looks as follows. So these blue blocks on the right, they represent a single F move. So this is the gate that performs this F move that I mentioned a few slides ago. So what you would do is you would use an ancilla that you would entangle, and you would use this to grow a bubble, which you would then stretch out by a sequence of F moves until you get this tube shape. This would then be measured in the appropriate basis. And then you would do the inverse of all these, of this first half. So you do all these F moves in reverse to get back to your original lattice. So this is a pretty big circuit, but it can be cut in half using some tricks. But this is the cleaner way of doing it. So the things I mentioned, so let's go back. These circuits I mentioned are for measuring the anion label of a plaquette. But this is only well defined within the subspace where no vertices are violated. So of course, when your code is subjected to noise, it's very well possible that some error happens which will take your state out of the subspace. And this seems like a problem, but it can be solved, since if you measure all your vertices and all these tail qubits as well, then you can condition some unitary operators on these measurement outcomes to get your state back into the stringlet subspace. So what we do is we measure everything, and then depending on the outcome, we apply the right circuits to get back to this stringlet subspace by fixing the violated vertices. So here's an example of such a circuit. The left is just the labeling of the different qubits. The middle part here is just the measurement circuit for a vertex term. This was designed by Bonsi and Di Vincenzo. And here on the right is an example of this vertex fixing. So if on the picture on the left, you would find that the top and the bottom vertices are violated, and you would find that your string qubit, or your tail edge, that your tail edge is in the 0 state, then this would be the circuit to fix it. As you see, this is a pretty simple circuit. It's just flip 3, 4, and 5, except if 1 and 2 are both in the 0 state, then only flip 3 and 5. So all different possible circuits that you can need are all pretty small. The biggest one only has depth 4. So in general, the error correction protocol splits in 2 parts. Well, once your system has been subjected to some noise, you would then first measure all your vertices and all these tail qubits. Then depending on the outcome, you would apply the right vertex correction. And then you're back in the stringlet subspace. So then we can go on with the second part, which starts by measuring the anion charge in all your plaquettes. And then if you find any non-trivial anions, you would give this information to your decoder, and your decoder will tell you which pairs of anions to fuse along which paths. You then do these fusions, and then you measure the fusion outcome. Since this is a non-abelian model, the fusion outcomes are not determined beforehand, so you need to measure whatever comes out of these fusions. You then feed this new information to your decoder. It will give you new pairs of anions to fuse, and so on. So here's an example of such a decoder. So a decoder we call a clustering decoder. This is not something we came up with, it's an existing model. So this is a decoding graph. So every vertex here represents one plaquette in your actual model. So this plaquette may or may not contain anions, and the ones who do have been indicated by these gray dots. So you would grow a cluster around each of these affected plaquettes, and then you would merge all overlapping clusters. Then you would fuse all anions inside each of these clusters. You would then measure the fusion outcome. So here there's only 2 of them that did not fuse to the vacuum. Then you would grow all the clusters, merge the overlapping clusters, and then you are at the beginning, so you fuse all anions within each cluster, and so on. So if you want to classically simulate this code, so this is the hardest part of this thing. You cannot just keep track of the state of all your qubits. since of course this would be much too complicated. Instead, we need some way to translate noise on the level of individual qubits to processes involving anyons. So instead of keeping track of the full state of all your qubits, you then keep track of the fusion state of the anyons that get created by your noise. To do this, we use the fact that fusion states of anyons in your different plaquettes, so the red lines represent the fusion tree of anyons in different plaquettes, and these fusion states have a one-to-one correspondence with states of your qubits. These are then very complicated superpositions of qubits, but there is an exact correspondence to a fusion state with anyons and a superposition of qubit states. Furthermore, if you take a fusion tree, which includes all your plaquettes, all labelings of this fusion tree corresponds to a set of states which is exactly an orthonormal basis of this string net subspace. So this means that this translation between noise on the level of qubits and processes with anyons is just a basis transformation. So what we need to do is we need to express the action of noise, vertex measurement, and vertex correction in this anionic fusion basis. So we need the following matrix elements, the ones shown here below. For those wondering, the bottom one is necessary in your simulation since you need a way of sampling measurement outcomes for vertex measurements. So you need this probability distribution. So after computing, so the question then first is, how do we compute these things? Since these fusion states are extremely complicated if you consider them in your computational basis of your qubits. So this is a very non-trivial task. So we'll be using two things to do this. First, these matrix elements should only depend on local properties of your states. They should not depend on the anion charge of some plaquette far away. So for example, here on the right, this is the case of a sigma Pauli X error. It should only depend on the anion charge of the plaquettes right around it, and then the way in which these can fuse and their total charge. It should not depend on anything else. The second thing we use is that these complicated states can be expressed as a tensor network state. And these tensor network states, they have the same structure as this fusion tree on the virtual level. So by using these 2 points and then throwing a whole lot of tensor network machinery at this, you find that these matrix elements can be calculated as the contraction of a finite tensor network. And so with enough care and patience, you can calculate more or less all 8.7 million of the non-trivial ones. And then you can use this to classically simulate the effect of noise on your model. So here's the assumptions of the simulations we did. First, noise is represented by random Pauli errors on individual qubits. The errors on a single qubit follow some Poisson process with a fixed rate, which we call P. So the total number of errors, which we note here as T, will follow some Poisson distribution with the mean given by the product of the number of qubits in your system times the rate of the errors on each of them. We assume that all measurements are perfect and instantaneous, and we assume that the recovery operations are also perfect. So our simulation would work by, first, you pick the number of time steps that you're going to simulate. So T is picked from this Poisson distribution and is the number of errors that will happen on different qubits. Then each time step in your simulation consists of the following steps. First, you select some random edge, so some random qubits. You select some random Pauli, and you apply it to this error, to this qubit. Then all vertex terms and all tail qubits are measured. Then, depending on the outcome, the right unitary to correct the violated vertices is applied. And then finally, the anion charge of all your plaquettes gets measured. So with these assumptions, and using this cluster decoder, which I mentioned earlier, we get the following results. So these plots here represents on the x-axis, you see this is the error rate of an individual qubit. And here we show the logical failure rate. on the y-axis. The different curves correspond to different system sizes. By the way, I forgot to mention, our code is put on a torus. So it's like the generalization of the toric code, essentially. So L here is the length of the shortest cycle in your torus. And then what we see here is very clear threshold behavior. And not only is there a threshold, it's actually really high. So people expected the thresholds to be non-existent or very low. And what we see is for depolarizing noise, we find 0.0475. So this is comparable to the surface code with similar assumptions. So this is not only surprising, it's actually very good news, especially when you consider the fact that this is done with just a Monte-Carlo simulation with some decoder. This is not some analytical bound on the optimal threshold. There might be other decoders which do better than this. So let me conclude with a summary and then some ideas for where to go from here. So we studied active non-abelian quantum error correction. So it's a system of qubits, a code space defined as the ground state of a slightly modified leveling 1 model. We use three things. We combine quantum error correction, topological quantum field theory, and tensor networks. And only combining all of these could we find a threshold. And this is actually the first threshold for a code in 2 dimensions, which natively supports a universal set of gates. Furthermore, it's not just a threshold, it's actually pretty high because it's comparable to the surface code thresholds under similar assumptions. So where to go from here? We really hope this opens the door to much more research on non-abelian codes. There's many directions to go. Just for this project, the obvious next thing to study is generalizing our simulations to a fully fault tolerant setup. We could also look into better decoders, different noise models. Then there's also other codes that could be studied. Our codes have pretty complicated measurement circuits with pretty high depth. There could be other non-abelian codes based on, for example, the quantum double model, which are simpler. Then you could consider a planar version of this, where information would be encoded well, you would have punctures containing anyons, and then your information would be encoded in the degenerate fusion state of these anyons. And then maybe the most exciting one for me is thinking about some realization of this. So the circuits we need are very high depth. However, if there is a way to do some multi-qubit gates very efficiently on the hardware level, these circuits suddenly are not so big anymore. So this would be the first step, kind of realizing these F moves as an efficient shot, in one shot, as an efficient thing, would really open the door to any experimental realizations of this code. So that's it for me. I hope I convinced some of you about the importance of studying non-abelian codes. And yeah, I'm ready to take some questions.
Thank you very much, Alexis, for the wonderful talk. There's a bunch of questions going on in the Slack chat. Barbara Terre Hall, and I think some of your co-authors have logged in and are helping answer, but I'm not sure if I should repeat some of those questions because I believe they've already been answered, but maybe I'll just ask you about something you mentioned in your question session, which was in your summary slide. You mentioned planar string net codes. What are the prospects for, I mean, your simulations all involve a torus. What can you say about codes that are planar?
Well, so well, we happen to have discussed this before, but you cannot just like do the same thing as on the surface code. So it really needs to happen with punctures containing anyons, and then using a degenerate fusion state. So I don't know exactly for the necessary steps to simulate the planar version of this, but it's certainly something we will look into. We haven't really explored that yet.
I suppose the first thing you would need would be to choose an encoding.
Yes,
right?
Yes.
And, I see.
Yeah, here, like on the torus version, all you need to do is just check if any errors that happens percolate around your torus.
Non-trivial, yeah.
Yeah.
Well, that's a first order decoder. Of course, there are high order things, but presumably these are suppressed and you don't actually need to correct them, right?
Yeah.
So someone, Michael Vassmer asks, is your simulation code publicly available?
Not yet, but it's a very good question. We plan on releasing it to GitHub, but we're still cleaning up the code since it's a lot of code. Like we need to add some comments here and there and clean things up, but it will be available on GitHub.
All right. Well, we've got you on record saying that now, so the pressure's on.
The pressure's on. Yeah.
That's good though. It's a lot of work cleaning up code, but it's a great resource if you can do it. Someone else, Tom Scrubby asks, my understanding is that the logical gates in this code are performed via Dane twists. Do you think these operations can be made fault tolerant? It seems like they will map local errors to non-local ones.
To be very honest, I'm not super well versed in these things. I think there is a way, but I'm sure one of my co-authors would be very eager to talk about this. Like Guanyu is
in the Slack chat.
Be an expert on like applying Dean twists.
Right. And Barbater Hall asked about the necessity of applying the unitary operator use of the. Can you just say a little? I think it was resolved in Slack, but maybe you could just elaborate. It seems like you really have to actively apply this unitary, and that it's not like in stabilizer codes where you can defer a Pauli frame update until later.
Yeah, so let's
maybe comment on the prospects for fault tolerance. You got about 2 minutes before we have to start the next talk.
Okay, so the why this is so necessary, did I understand this well?
Why is it necessary? And then is it necessary? If so, why? And maybe you could comment about the prospects for fault tolerance using these ideas, and maybe fault tolerance simulation as well, which I think is linked to the answer to this question.
Yeah, so the need for this arises from the fact that essentially before correcting, you want to see these excitations that occur as anyons. And you can only understand these things as anyons. This only makes sense and is only well defined within this subspace where all your vertex conditions are satisfied. Once you leave this subspace, it's just a mess of very complicated superposition of states. So so before you can understand this mess of a state as, oh, this is just some anyons living here and there, you must go back to this subspace. In our simulation, we did this like between every error, but in practice, you don't need to do this, right? You can just, noise happens, and then you do all your measurements, you fix your vertices, and then you can go on. We haven't really worked on the prospect of including measurement errors into this thing, since these are necessary before you can measure actually. I mean, these things must be applied correctly before you can measure your anion charge correctly. So we're still working out how that would happen. But I would love to discuss more on this if there's some more time later. Maybe.
Yeah, I would love to discuss fault tolerance, especially since the measurement circuits have some non-trivial depth here because you have to recursively fuse and things like this. I think there's a lot of interesting and challenging open questions.
Yeah, there's
unfortunately we're out of time. So I'll just remind everyone that at the end, we're going to have the roundtable discussion. I'll send the links out for the roundtable discussions, and then we can ask anybody anything. Sorry, people are posting in the chat. We'll be able to ask our speaker anything we want at the roundtable.
I'll be available.
And after the next talk.
Yeah.
So let's thank our speaker one more time.